Okay. All right. Okay, so slightly different. I'm not going to kind of show you where we get these equations. You can watch. I posted two videos online of how you get. Oh, I wanted to load the other one. How to get these equations? Okay. Um, Basically, what we're now looking at, and really the next 2 days, and then the take home. I might have one, but it's going to be very similar to like an in-class problem. Okay. You know how before we had conservation of mass equation, summation of m dot equals summation in and out, okay? And then these are forces. So some of the forces in the x, some of the forces in the y, some of the forces in the z. Okay, do you remember when we had the momentum analysis equations, we had to find the forces shooting out of the fire hydrant, that one homework problem, okay? Well, some of the forces in the conservation of mass are for, like, you can do those equations to figure out forces on the outsides, okay? If you want to know what's happening inside that fire hydrant, okay, and the water just inside before it shoots out to the atmosphere, you have to look at what they call a differential analysis, okay? So these are the exact equations. The conservation of mass is now called the continuity equation, okay? These are called the Navier-Stokes equations. They're forces in the x, y, and z, okay? These equations are used to solve what's happening in the fluid inside the fire hydrant, okay? Or a liquid layer that we're going to do a few problems with, okay? And if you really want to know where they come from, watch my videos. I posted two of those online. It kind of shows you how these equations are derived, okay? They have to look at a little differential element like a cube, and what's coming into the cube, coming out of the cube, and it gets a little tricky, but it's not too bad. But I don't want to spend the time in class. I want to make sure, okay, here's the continuity equation, which is conservation of mass in differential form. And these are the x, y components. And have these equations, and we're going to use these equations to solve a fluid flow, okay? So this one right here, I gave you two sheets. It's the same exact thing. I actually wrote them out because, I mean, it's much easier to have them in front of you than rewrite them, right? Okay, so you can make copies if you ever had to. There's going to be one homework problem. We're going to use these. Okay, you won't use them all. You use this one and these two. All right, and there's two questions I think on the homework. The other one is going to be on stream functions, which I'll talk about after we do some of these problems. Okay, and on Tuesday you can start working on them now, but on Tuesday I'll help you solve those. Okay, so this is more of let's see these, use those, and then move on. Because if you ever go to grad school and you're in this type of field, this is what you would use. The CFD, the answers you're using, these are the equations they're using pretty much in one form or another, okay? So they're solving these equations numerically, okay? And some of them are incompressible, so these get actually a little bit longer. They're a little bit trickier, okay? But for us, right now, you can do incompressible, and these are the exact equations, in some cases, in ANSYS, that they use to solve for fluid flow, okay? So U, V, and W represent what? Do you remember?
XY.
XYZ velocities, okay? All right, and then down here on the forces, the left side of these equations are really accelerations, okay? The right side are forces. This is pressure force. This is, what do you think rho g would be? Gravity. Okay, so you got pressure, gravity, and then when you have mu, what do you think that is? Viscosity. This is viscous forces. Okay, so left side of these forces are accelerations. The right side are forces. So sum of the forces equals ma. But you have to look at fluid flow. Okay, why are they partials? Remember why they're partials? Well, these accelerations or these velocities are functions of x, y, z, and time. Okay, so it's a fourth dimension kind of thing. Okay, we did that a long time ago when we briefly talked about momentum analysis, okay? But as long as you kind of understand, okay, here's math, and I'm going to show you a problem and talk about this, all right? And then in these equations, acceleration on the left, or MA terms, and on the right, you have forces, which is pressure, gravity, and viscous, okay? So let's do this first problem together here, all right? And show you how we can use those to develop a velocity profile. So here, you have a liquid layer, you have a plate that's fixed at the bottom, and you have a plate that's moving at the top. All right? You've seen this problem before. Regular fluids. Okay? You see how this gives you a linear velocity distribution, and we figured out a drag friction equation? Well, we can get that. I can show you what this velocity profile is using these equations. Okay? So this problem, we have a fixed plate, the plate's moving. We want to use Navier Stokes and the continuity equation to develop a relation for the velocity profile. Okay? So let's go ahead and do that. Oh, something happened. Try to use that as my, doesn't yank my computer, but I think it is. That's fine, I'll do it like this. All right, I'm going to take a snippet of this. And let's paste this here. Okay, so we're going to assume 2D, x and y. And do you see why there's no z equation? There's no z. We're going to assume steady state, and the flow is fully developed. Do you remember what that meant? Yeah, because you know if fluid starts in a pipe from a tank, it takes a while before it gets to fully developed. All right, let's look at the continuity equation, which is this. This is mass. If you look here, what direction is the velocity only in? X. And we call that the u direction, right? Those two are gone because there is no velocity up, which is in the v, and the z direction is gone too, right? So what do we have? We have from that we have du dx is 0. What does that tell us?
That x component of incompressible Navier Stokes equation that u times du over dx is 0.
Yep. But it also says
There's no
that
acceleration.
that if you change your x location, the change in u is going to be the same, right? It doesn't change. Okay, so if you picked a point here at x of 0 and you picked another point at x of 10, okay, those velocities will be the same at a certain y location, right? Okay, and if you look here, it actually says u is a function of y, meaning that the velocity at this point changes in the y direction. Okay, so far okay, sort of? All right, now let's look at these Navier-Stokes equations. Start with this first one, du dt. What's that?
0.
Why?
Because there's no t.
Yep. What is the assumption we picked?
Oh, okay.
Well, fully developed is steady state. That term's gone. What about u du dx? Why?
Because du dx.
Because from the continuity equation we said it was 0. Yep. So v is 0, right?
Mhm.
That's the reason why. But du, dy isn't. But that term is gone. There's no z direction. Yeah. No. This is how these problems are, right? Okay. Gravity doesn't act in the x, right?
My homework again for toilet bowl works.
Okay. Now I just skip that for a second. What about u dx, the second derivative? Still 0, right?
No.
What about du dy?
It's got some.
That's something. We don't know that. And there's no z. And what about this y direction down here? Or this y component of the v velocity? Is there v at all?
No.
No. Oh, that's garbage. Okay. And the problem states above what? Oh.
Get that part. U equals 0, but V equals W equals.
Yep. Keep reading. Next sentence.
The present case has the upper plate moving at a velocity v, but there's no pressure gradient.
What does that mean? For
No pressure.
dp dx?
0.
0. Okay. Well, that wouldn't be, but there's nothing in this. Like we don't even need this equation at all. Yep. Yeah, technically that wouldn't be. That would equal 0, right? Because rho gy equals 0. Okay. So the only thing we have is 0 equals mu dy, right? Which is actually, you can switch to a single derivative, right? Why? It's no longer partial because u is only a function of y. So it becomes a total derivative. And what happened to the mu? It goes because it's equal to 0. Oh, it says in the problem, no pressure gradient. The last sentence, well, third to the last sentence. And we neglect gravity effects, huh? Okay. You see how, okay, so you have the continuity, which is mass, okay? Then you have these, which are forces. And what you need to do is you need to look at every term and figure out what you can cancel and what you can't cancel. Then you end up getting, what is this called? Differential equation. How do you solve these? How do you solve that one?
Differentiate.
That one's easy one. You've actually done this. Some of you who've taken heat transfer. Everybody but Alyssa and Garrett. And you haven't. Oh, okay. I didn't know you were. You've done that one, right?
Yeah. Well, you're the master. Come on, man. Let's go.
Come on.
This is all you, Will.
Tell me. This is the easiest. Actually, this is only Calc 2 stuff. So what do you do in Calc 2? No, easier than that.
Easier.
No,
No.
not even the chain rule. Easiest rule in Calc 2. Well, what do you do in Calc 2? Integrate. She's going to integrate how many times?
Twice.
Twice. So when you integrate the first time, you get a constant, right?
Mm-hmm.
You integrate again and you get, whoa, u equals c1y plus c2. Right? Does that make sense? Integration? We just integrate twice. You integrate the first time, you get the derivative, but that over here becomes a constant, right? Yep. I'll help you.
Yeah, well, it's going to be the biggest help here.
I know this engineering isn't your forte, but
Yeah, flying planes is.
heat transfer, well, yeah, I mean, this becomes what? T becomes C1x plus C2, right? Okay. So look at this equation. What does that represent? What type of relationship? Linear. Look at the graph that you created. Is that linear? Yeah. Well,
So is that your check?
yes, you could kind of see, but if I took that out, you wouldn't know, right? But from the first fluids, you remember that a fixed, and this is moving, you should get a linear profile. Okay? So if you look here, we're using these differential equations, differential mass, forces, to figure out a differential equation. We solve that differential equation. Now the question becomes, how do we find C1 and C2? This is good for students. I know, Garrett, you're not in DiffQ yet. Are you in DiffQ yet? Okay, so this is good. Most everyone else is taking DiffQ. Okay, so this is a good review for you, but also a good prequel for you, what's coming up in DiffQ. Okay. Are the initial values?
No.
What are they called? So we have this equation. We need to figure out the exact equation. I know, that's why I'm trying to help you. If I told you time, that would be what? Initial conditions, right? But if I told you positions, what do you have to apply? Boundary conditions?
Boundary conditions.
Boundary conditions? I hear crickets. No? Do you remember this?
Wow, you was rough.
Yeah.
Put that
Okay.
out there.
That's fine. Is it making a little bit more sense now? Okay. Why?
Because he never paid attention.
You see this right here? I'm going to ask you, Will, what are we solving for? U, because it's on the top, on the right of the derivative. What is U going to be a function of?
What's U a function of? Why?
It's going to be whatever's on the bottom. Okay, so it'd be Y. This one is actually second order, because it's 2, homogeneous, and that's it. And it's actually separable, meaning you separated these variables, and so all you have to do for that rule is integrate. All differential equations is rules. Once you identify this, you just go to the book and find the rule and do it. Okay? So this one is the easiest out of all differential equations. You just integrate twice, and you get your value. Now, in order to find these values, you need to apply boundary conditions. And now I kind of wish I was teaching vibrations too next semester. No one. I usually do it off every other year. But this differential equations, you would really understand how to do it, because that's all we do in that class. So can someone tell me how many boundary conditions we need?
2.
Why 2?
I couldn't tell you.
Okay. We need 2 because
There's two
there's 2 constants, but it's also how many orders?
orders.
2, second order. So you need 2. Okay? Okay, I'm going to wait for a second. I'm going to show you something. You all right, Alyssa? Oh, okay. Okay, I can show you on. I can show you. All right, I'll go back to this. Okay. Remember, did I do this problem with you, the spring and mass, before? With this K and this M? And we had a differential equation that.
Bond graph theory. Let's do it right now, Chris.
What?
That's really easy, actually.
Remember we had that differential equation? And then we can find a solution. And I'm going to show you something on a graph. So this is vibrating back and forth. What do you respect, or what would you think you would see on a graph if you plotted x versus t? It would oscillate, right? And it would be the same amplitude. So in this solution here, A is amplitude, so high from the 0 up. And this phi is like, you see how this doesn't quite start at 0, the sine wave, it's moved? That's just a phase shift. So that's just information. But this is second order. How many initial conditions in this, because it's time, would you need? 2. Anytime, second order, you need 2. You always need 2. Third order, 3. Fourth order, 4. Where do you see fourth order? Anybody want to guess? Deflections. Deflection differential equations are fourth order. Okay, you need. What happened? Still good. Okay. So we need 2 initial conditions. What do you think? How do you know what? Can you give me an initial condition? Like what are they?
Like at time 0.
What is the x value? Correct. I see where you're going. So x at time of 0 is, I don't know, let's say it's 1 millimeter. Okay? So the first initial condition tells you where it starts at 0. What does the second initial condition tell you? You could, but not with initial conditions. That's for boundary conditions, and I'll cover that. How do you know which way is it going to go up or is it going to go down?
Now.
So it's going to be the derivative, right?
Right.
At time of 0. And say that's 0, I don't know, or 0.1 or something, millimeters per second. So the slope is the derivative. So that's why you need 2. You need to figure out where you start and how you go. Okay, does that make sense? Boundary conditions are what happens at this point, position, and the other point. Okay? So these two will have numbers. So if we apply boundary conditions, if you look at your sheet, can someone tell me what at y equals plus h, what u equals?
Minus h.
No, velocity.
Oh, velocity-wise?
What's it moving at plus h? What's the velocity of the fluid? V, yeah. In your paper, Will? You see the top at plus h, the liquid sticks to that plate, right? And it's moving at v. What about the other boundary condition at equals negative h? U is 0. So those are our 2 boundary conditions. I'm trying to give you a good review, too, of DiffEQ. So if you have questions, please ask. Does it make sense? Some of you, I know, listen, Garrett, are kind of haven't taken it. But does it kind of make sense where we're doing these? Okay. Who else? Anybody else have questions? How do we apply these boundary conditions? We plug them into our equation. So let's do, I'm going to call the first one 1 and the second one 2. So let's apply the first boundary condition. So that states that U is equal to V at H. Okay, so let me write it here. U equals C1Y plus C2. So I just plugged in V for U, and I plugged in H for Y. Can we do anything with that? No, we need the other one. Apply the second one, which states that U is equal to 0 at Y is negative H. So 0 equals C1 times negative Y plus C2.
Why don't you do negative h there?
Oh, yeah, yeah, sorry, negative H. Yep, thank you. I don't know why I did that. How many equations do we have?
2,
How many unknowns?
4,
2.
16.
2. So C1 and C2 are unknowns. We have two equations. We can solve for C1, which is V over 2H. We can solve for C2, which is V over 2, in terms of velocity, okay? And then we can finally plug that back in. So U becomes V over 2H y plus V over 2.
That's it.
That's your velocity profile, yep. Different, right? A little bit different. But this is where you actually apply differential equations. Okay? So now we know what the velocity profile, or we know the details of velocity profile between those plates. Okay? How do you find the friction force? Well, I'm going to show you here. Here's this plate again. Here's the profile. And let's take a small little rectangle piece. Oops, I'm going to blow it up a little bit more. And what we have, magenta, is we have shear forces. Tau xy. This would be tau yx, and this one down here would be tau xy. So you see that there's 4 corners, right, of this? Each one of those lines, okay, will have a shear. And you see how the subscripts are like yx? The y, the first one indicates the y kind of direction. Okay, so it's in this plane, but going in the x direction. Okay? Where the xy is in this location, but going down or up. Okay? Now, this is something I didn't give you, but we can write it. And this is going to be a 3 by 3 matrix. Yep, tau ij, yep. Okay, yep. So this is mu. Two. Yes, that is a 2. Yes, my z's will be like that. Yep.
do have a question really quick on what we were doing earlier. Are we gonna look for the particles to kind of eliminate like that so that we're left with one term?
Most of the time we're gonna be, or two terms. The next problem I'm gonna do has pressure and that.
Okay.
Yep, yep. Shear force, so if you notice, I have X, Y, and Z, right? That's why this is a 3x3, because shear force acts on every single plane of a cube, right? How many sides are on a cube? 6. Let's see here. 1, 2, 3, 4, 6. Yeah. So how many? So on a square we have 4, right? So you'd have to add. How did I do that? 1, 2, 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Yeah, my the video will explain a little bit more where they come from. But this, so you how much? So the forces are acting on. You have pressure, you have gravity, and you have shear. Okay. If you wanted to know the pressure, and we're going to continue this in here in a second. This is just another thing. P, that acts normal, right? This one's easier. Where'd it go? That's okay. I'll continue here in a second. There we go. You can write it in terms of a 3x3. Minus P 0, 0, 0, minus P 0, 0, 0, minus P. So you have pressure, you have friction or shear forces. Then you also have gravity. So those are the three main forces acting on anything. Pressure, shear, and that. But this only acts normal. So it only acts in the X, Y, and Z directions. That's it. Poo, I did write poo. What's that? No, that's just saying that pressure only acts in the X, Y, and Z. You see how these are all V, D, Y, and W? They're only the X, Y, and Z because they're always normal. There's no side forces, okay? We can use this, the one on the left, to figure out what the actual shear force or friction force is. So let's go through each term here. What did we say du dx was in that problem? 0. Okay. How about the second term? So you have mu. And can someone tell me what du dy is? What was u equal to? V over 2h times y. So if we wanted to take the partial of this equation with respect to y, what is it? V over 2h. Everyone see that? Just taking the derivative of u with respect to y. What is the derivative of v with respect to x? 0. It's not even there. Okay? Next term. Du dz. 0. W dx. 0. Okay? Bottom middle here. It's very similar to that one, right?
Zero.
The first term is 0, but then you have du dy. So that's exactly
It's just the
b over 2h. Let me write it just like we had this one. So mu v over 2h. All right. And you keep going. That would be 0. That would be 0. All the rest are 0. So ty, or tau xy equals tau yx, which is mu v over 2h. So if you go back, we're almost there. If we go back to this sketch, do you see why the top and the bottom, this yx and yx are 0? Okay. Wait, was it 0? No, not 0. So that's what I meant, not 0. Okay. And these are not 0 because of this profile. Okay, because you have a linear profile, you're actually going to get a shear force of the liquid layer inside there. Okay? It's going to like pinch it. So this shear force, we want to figure out the friction force. We multiply tau by the area. So mu v over 2h times the area. You've seen that before in the first fluids. Actually, I told you that tau was the derivative, okay, or actually mu times the derivative. So what we just did is we took the differential elements, we found the velocity profile, and we now have the friction force developed in that liquid layer. Okay? That's the area that the liquid touches the top of this plate. So where is the, that would be this projected area here. That's the area that the liquid touches that surface. Yep. Yep, 2 plates. That one's moving and that one's fixed. All right. So just to remind you, you can use differential analysis to figure out anything about the details inside this flow. You can then find velocity and you can find force or friction. Okay? Okay, let's take a 5-minute break and we'll do the next practice problem in your paper, okay?
Go up.
Where did it go? Okay, so now here both plates are fixed and there's a pressure varies in the x direction. So find the velocity profile. So in this one, that looks really familiar, right? It's pipe flow. Okay, so we know that pressure here has to be higher than down here in order for it to go, because it has to overcome friction, right? So we're going to assume, again, steady state, 2D, and fully developed. All right, so let's look at the continuity equation. Which direction is there V and W? No. So again, du dx is 0. Because u is only going, it's going in the x direction, but it only changes in what? The y. Okay? So let's now look at the x component of the Navier Stokes. First term, du dt. 0. Second term,
Gone.
gone. Is there a v velocity? Nope. So that is gone, and there's no z. Okay, but there is a dp dx. We know that changes. There's no gravity in the x. This second derivative is 0, and there's no z. Down at the bottom, 0, 0, 0, 0, 0. Well, yeah, no gravity effects too. So based on this one, dp dy equals 0.
You just switch.
So what does that tell us about pressure in the y direction? Doesn't change. There is no pressure gradient in the y direction. It only changes in the x direction. And it's going to be constant, yes. So based on this equation here, we have 0 equals minus dp dx. Why am I writing on a tilt? Plus mu times the second derivative of u over y. And I'm going to change it to big derivatives. And while you're writing this, think about, do you remember in fluid power lab, do you remember the pressure change over X? You remember that at all?
Yeah, no, they're not.
That term right here that I circled is actually a constant. So if you pick X at 0 and X at 2, you're going to get the same delta P as if you picked X at 5 and X at, how far did I go for X? 0 to 2, so you add like 2 more, okay? Yeah, so 5 to 7. You're going to get that same change in pressure, okay? So technically we have d squared u dy squared equals 1 over mu dp dx, which is a constant. So how do we solve, what is this now, a differential equation? And it's separable. Yep, because we separated them out. And we just do what? Twice. Integrate. So the derivative, because we integrate, is 1 over mu dp dx times c1. And then we integrate again. We get 1 over mu dp. Oh, I forgot. What did I forget here? I didn't integrate right. Times y plus c1. And this is y squared over 2 plus c1y plus c2.
Why did you see one now get a Y?
Because you integrate that. So we integrate once, then we integrate again. Each term you're going to add another y to, plus a constant. So this term on the right on the first one that I circled in red is just a constant. So that's why you add a y here. Then we plus c1. Then we integrate again, and that has to become y squared over 2 plus c1y plus c2. That is our profile. It's nonlinear, which it should be, right? It should be it's parabolic. Okay, now what do we need to do to find C1 and C2? Apply boundary conditions. at y equals plus h, what is u? 0. What about at minus h? It's also 0. You see a pattern? You find your differential equation, you solve it, you apply boundary conditions to solve for the constants. That's what differential equations are. And when you do this, I mean, you're going to have to do it for the homework for another problem, so I'll just write what it is. But you apply those, and you get this for your solution after some algebra. Okay? So, in this y direction, we have velocity. Once we find velocity, what can you find? You can find acceleration, sure, but you can also figure out shear forces. And you already know the pressure force is constant, dp dx. Okay? Okay, how would you know? So we said that dp dx is a constant, right? How do you find P alone? The pressure at various points. Huh? Integrate. P equals C1x, right? So you'd have to figure out what that constant is, and it depends on the pipe size and diameter and stuff. But if you want to know the pressure at every point, okay, that's your equation right there. How do you find the shear force? That 3 by 3 matrix, right? So you go through each term of that 3 by 3 and figure that out. So now you can find friction forces. All right? So I wanted just to kind of, and it's okay if you're still a little stuck, go through these at home and see if it makes sense. Okay, I'm going to stop for today. We'll talk about stream functions on Tuesday, and I'll help you set up. I'll review these, and we'll start working on the homework together. Okay. By the end of that day, you'll have your homework almost done. Okay, and then we'll review next Thursday. I'll give you a take home. That'll be due the following Tuesday. So.